The first reporter will be Victor Nekrasov from STT Group Russia. He will speak about the experimental complex of georeferencing of images from spacecraft. Good afternoon, dear colleagues, distinguished moderator. Now I'll speak about the experimental complex for improving the georeferencing accuracy of spaceborne images. This work had been done upon the request of the NEM Corporation. This is the main executing agency and main developer of such spacecraft. In fact, these are twin brother spacecraft. They have indistinguishable characteristics in the camera parameters, but they have very similar platforms and similar equipment. They're designed for various applications of monitoring. That would be emergency monitoring, forest fires, some natural disasters like volcano eruptions or earthquakes, and one of the goals of the system is cartography or mapping. But for Canopus B, mapping is not a priority goal. It was mentioned that mapping is at the bottom of its priorities. But for another one, for another spacecraft, mapping is the primary objective. Later on, I will keep speaking about Canopus B, but I will generally speak about both of them. This is the general overview of the spacecraft. You can see right here the star instruments, and here we have the module of the equipment. This is the brief list of specs of these two spacecraft. They were born, both of them, on July 22nd. Let's hope that in 13 years we'll be able to celebrate the next anniversary, but still their life expectancy is 5-7 years. They were launched from Baikonur, and due to the delays and some other things, and there was a group launch. 6 spacecraft were launched simultaneously. 2 of them was Canopus B and KA. They could be considered to be small ones, about 400 kilos each. They almost round orbit, which about within 500 plus kilometers. So the satellites are always oriented towards the sun. That's why the battery is for 300 watts. That's how it works. The obliqueness of the orbit is 97 degrees. The thing is that the flight plan is done based on our data, and for that we use one kind of obliqueness. But the NARAD system from America identifies a somewhat different degree, and we could have a small problem because of that, because the orientation is done based on the coordinates. And the different angle sometimes can introduce certain variations. So this is one of the peculiarities. So far, they're not fully compatible, these two systems. Anyway, the frequency is 15 days. The frequency of flyby is 15 days, as I told you. Orientation regimen is 3-axis based. It is quite known that for mapping the best way to shoot images is in nadir. The redness rate is 3 minutes. It means that that's how much time is needed to stabilize the platform. Yet, if it will turn to 40 degrees or 80 degrees, of course this time is increased will double at least. Both satellites have the same module of the target equipment, of the payload. It was developed by Pelling, Belarusian company, and they have installed 2 cameras there. One camera was PSS, Another one is MSS. PSS is panchromatic system. MSS is multi-spectral imaging system. It has 4 bands, and the ground sample distance is 2.1 meters. For MSS is 10.5 meters. But is an average, of course, number, because altitude can be different, and the resolution is still being tested. This equipment is being prepared for operation. So far, based on the preliminary measurements, it would be somewhere from 2.5 to 3 meters resolution, but this is still preliminary data. Whatever numbers I mention, you still have to take it with a grain of salt, because with additional testing we improve the accuracy and so on and so forth. Everything is work in progress. As I told you, MSS has 4 spectral bands. This is standard RGB and near IR bands. It's about 23 kilometers for PSS. This is the coverage swath, and this is the view of the payload on the frame before it is installed in the satellite. The peculiarities of these cameras: PSS camera is panchromatic with quite high resolution. It contains 6 matrices or 6 arrays in the same focal plane, but they do not overlap each other. There are quite big gaps between them. And that's why the homogeneous image can be acquired only when all 6 arrays are acquiring image. And MSS has 4 arrays arranged in a row. That is why the fully colorized image can be acquired only when the same place is acquired 3 times by different arrays. This is perhaps the very first image acquired by Canopus B. And the first image was used. It was acquired in August this year in Bahrain. Most of this image is in sea. The uniqueness of this is that we have acquired the image of the plane. This is the second image from the same route. Again, virtually the only image we have acquired. We have missed the land. This is Greece, actually. This is the place not far from Athens. We want to capture Athens, but missed about 16 kilometers out of city limits. But still, the airport looks quite good. This is synthesized image, which combines both PSS and color images from MSS. Everybody realizes that this is a Photoshop product. And this is the bokeh image. The thing is that at the first, all the tests, bokeh was very unlucky with cloudiness and everything, but this is the first successful image. This is also a synthesized image from colorized channels and PSS. This is Dubai. That's why you can see this beautiful palm tree there. And these images are available at Roscosmos database. You can look at them at better resolution. This is Canopus B, the same route over Dubai, and we found a beautiful airport there, also synthesized image. And on Thursday, just before coming to this conference, we were acquiring images, and I found an archive Iconos picture, and here you can compare Iconos with Canopus B. I'd say that one can compare, but you have to take into consideration that Iconos has a meter resolution and Canopus B has 2.5 meter resolution. Here you can see how these microframes cover El Riyadh. It is quite clear here that, yes, perhaps you can see it here, that the images go to different places, because now we are flight testing it. and this testing will end by the end of the month. So it has roughly chosen this orientation, and the frames do not coincide with each other, but still it's quite good. Here you can see the Dubai route, and it was precise orientation, and this is a good example of how we have precisely oriented these frames. This is Kamchatka. A plane crashed there, and they asked us to capture images of Kamchatka, and this is Krasnoyarsk. In fact, this is the only so far our area which has been photographed by Canopus B. In fact, what I've shown to you just before the start of the conference, these are the only flybys which have been done with image acquisition. There were only 4 of them. Some of the flybys were done for metric calibration for internal purposes, and for our mapping purposes they're not applicable, unfortunately. Anyway, on this Krasnoyarsk picture you can see that white frames here would be the original orbital data. So basically we have to tie these images to original orbital data, but the red boxes are the images which have undergone our georeferencing, and the shift is about 3 kilometers here based on orbital data. So far the error is 3 kilometers. For Dubai flyby, the error was 300 meters. So far the complex is still being tested, and in order to resolve this georeferencing calibration we have developed a complex, GeoK, that's the name of the complex, based on the terms of reference. Even if everything works well and fine-tuned, the final precision of angle orientation is about based on the inconsistencies or lack of precision of GLONASS, and it's about 150 meters. And the instruments for the modern system, that would be still too high, and that's why we decided to build the additional complex to calibrate the georeferencing of data. We did it to maximize the automatization of the process. In what way? We can use the raster basis and some of the procedures which will georeference these images based on that. And eventually we expect to get the maximum standardized output which can be used in standard packages. So it would be easy. By pressing a couple of buttons you can do ortho transformation. And eventually we have set ourselves the following tasks. First, the development of formalized model of Earth imaging by different sensors of Ka. Then we had to develop a method of formation of RPC. We just had to, they are known, but we had to adapt them to our circumstances. And we also had to use the images of high resolution to use precise data. And eventually we had to develop the technology of mathematical modeling, because in fact we believe that such a complex could be applicable not only for Canopus B spacecraft but for a broader range of other satellites. Of course, we're not talking about GI and Worldview, which originally can ensure high precision, but for many other satellites it's still quite relevant. What sources did we use to build the raster database of reference information? First of all, we used Landsat data and medium resolution images. These are high resolution images from GeoEye and Worldview. digital elevation model. SRTM we used, and there we have transformed the formats from GeoMaster, and whatever is higher than 60 degrees, DM is used there. So we used open sources for the databases. Some of these are commercially available, and that of high resolution. We try to use all the data that we have for Russia, because we were doing it for Russia. You can see the coverage of Russia with the images of 30-meter resolution, not so many of them. 15 meters resolution, we have coverage of almost the whole country. But Landsat 7 has its own deficiencies that after 2003, and the images are no longer coming out so well. That is why that after 2003, the number of images not so high. And these are the high resolution data about Serpukhova district in Moscow. This is the Leningrad region, not far from the nuclear power plant. This is Petyagorsk test ground. This is the main one, which it has enough high resolution data about it. It has about 220 ground control points, so this is but so far we haven't captured images of it. And the most recent information I acquired as of this week, we start the imaging this test ground. The raster information database, we expect to do it for the whole territory of Russia, and then subsequently for the world over. This is Petyagorsk test ground. We used in our work many algorithms. In fact, different images need to be processed differently. That is why I can write many dissertations and articles about this. I've just enumerated the main methods, the principal strategies that we have applied. Technological scheme of the complex is quite straightforward. The data are acquired and then goes through this intermediary stage. Then we have complex of metadata, which we transform. Then we extract from our database some raster map, which is used to fine-tune the georeferencing, and we get the RPC images. This is functional structure with more detail. And the first examples, here you can see, I've shown this image before. Here the image is referenced to the orbital data. You can see that there are some deviations, about 300-meter deviation. 320, depending on different microelements. After the complex of georeferencing, fine-tuning, we get some meter deviation. Cannot tell you for sure because we had many images, many frames, and the information is at the preliminary approximation only, so it's hard to tell you exact numbers, but still it's only meters deviation. Krasnoyarsk, you can see here that based on orbital data, there is too much of a deviation, about more than 3 kilometers. After georeferencing, we finally acquired the result of about 230 meters. And based on different frames, the deviation rate could be different. Both of these passes were uploaded into photo mod to their georeferencing module, and a block of images had been uploaded. I think my colleagues from Uniter will tell you more about this georeferencing exercise. And these are output products. Based on the terms of reference, we have to select only one product. RPC polynomial for our images. Already the complex allows us, although it is done in experimental mode, it helps us get RPC polynomials for the whole frame of PSS. 6 frames in the focal plane. We can get the equalized block of microframes. Again, would be referenced and tied to RPC polynomials and all the forms of transformed frames, full frames, half frames, and so on. And the thing which we're working on at the moment, we have some success, but not convincing enough, because MSS frames are formed as part of the movement, and there is certain gap between them. We do have some results, but so far not too good at the moment. Because at this altitude, the error rate is too high. Anyway, and the last thing that we have in our complex, this is the calibration mode of the imaging system. The imaging system is calibrated on Earth, but after vibration and temperature impact, there is a mode of calibration for our imaging systems. And in conclusion, we believe that the development of such a complex of georeferencing will help us address a number of issues related to the data acquired from Canopus. Not only Canopus, actually. I hope that it can help many other satellites as well. As a result, we acquire timely georeferenced information. We believe that it can be a fully automated process with minimum involvement of operators. I must note here that we need to use test grounds or test fields, not only the 5 of them in Russia. One of them is well measured in Petygorsk, but still these test fields are needed for calibration of cameras. We started this work by developing a model of image capturing and the software which will help us do this. Until August 27th, we used this model images for that, which allowed us to develop the calibration methodology. Very important thing is RPC. It's the coefficient of rational polynomial coefficient, because our users want to have more freedom, more flexibility to better process the data, and this RPC helps them do this. And of course the use of polynomials on the selected points. That's an additional objective which was set by us to assess the performance rate of the actual equipment. Thank you for your attention. If you have questions, I'm ready to answer them. Distinguished colleagues, I have a proposal. As long as our speaker has gone over time, let us ask him questions later on in more informal atmosphere. Now, let us wish the spacecraft Canopus and the team who are fine-tuning and flight testing it, let us wish them success so that they succeed in their project. Thank you.